It's a short week, no class on Thursday, just to remind you. I have been juggling the schedules to make sure that I give you enough time to work on things, so that's why we'll have a quiz due next Monday, and then first homework is not due until the 23rd. I will let you know when both of those things are ready, should be later today or tomorrow. First homework, by the way, is going to be over what we've been talking about, interaction terms. Yeah, it'll be fun, I promise. Or it won't be that painful. And to some of you, it will be familiar. I'll say that too. So we were talking about interactions. What do you remember from last time? I'll take words, letters, gestures.
More positive, less positive?
Yeah, more positive, less positive, more negative, less negative. What is that? What does that go with, those ideas? A slope. What happens to a main effect as a function of an interaction term? Yep. The main effects become conditional. That's another thing to remember. They are specifically when the interacting variable is at 0. So that's what's known as a simple main effect. If you have a predictor that is not part of an interaction term, that's a marginal or unconditional main effect. It means it holds regardless of any other value for a predictor in the sample. Let's see. We did some examples. I'll show you some more examples today. I think that's a good place to dive in. Let's practice interaction terms amongst continuous predictors, or quantitative variables, I should say, and then we'll look at what happens to categorical. So I'd like to jump in with example 2b, if you wouldn't mind. I had built this before I got a sense that everyone was going to be like all about Stata in this class. So it does have both sets of syntax for Stata and SPSS, goodness. Stata and SAS, but I only have SAS output. If you want to see what the output looks like in Stata, though, I have it as part of, there's a folder online. Let me show you where that is. Data, syntax, and output for examples 2a, 2b, and 2c on 9.3. That folder has all of the output from both programs, so you can look at that if you'd rather look at what things look like in Stata. All right. So do you have this? Yeah, okay. So this is continuing the data example we looked at last week with main effects. A hypothetical sample of older adults. We have age and grip strength as continuous predictors. We're also, in this example, going to be controlling for gender and dementia group, focusing on interactions among the continuous predictors for now. One thing that Stata does really well, that SAS does less well, is this idea of margins. You can ask for predicted values over a range. SAS does not allow you to do that very efficiently, and so I have created a workaround here that I called fake people. So whenever you know in advance that you're going to want to make predictions out of your data set, such as for making plots, which are probably the easiest way to depict what an interaction looks like, one way to do that is to create fake cases in your data set that have the values of the predictor that you want to plot. So for instance here, I am creating a new fake data set where everybody's ID variable is -99. You'll see that I have 3, 0, and -3 for grip strength. That's roughly plus or minus 1 standard deviation. -5, 0, and 5 for age. And then I'm holding the other variables constant. So this is for a man who is not going to have dementia. Then I merge that fake data set with the real one. And what happens is that I can ask the program to create predicted values. It will do so for every case in the data set, even the fake people, and then I have those predictions without having to write lots and lots of lines of code to get them. Because the fake people don't have an outcome, they don't hurt anything. So they're not used in estimating the model, but they are used in the post-estimation of creating predicted values. So this is a thing that we have to do in programs such as SAS or SPSS, where there's no quick and easy way to ask for predictions. So that's what that's about. So we're adding to the main effects model that we looked at last time. One new term. It's at the top of the second page here. So centering age is a continuous predictor at 85. Grip strength is 9 pounds per square inch. Men is the reference group, and the none group for dementia. There's our two contrasts separating none versus current and none versus future. And this is my new coefficient here, beta 6. So we know that this interaction term, beta 6, is going to change the main effective age as a function of grip strength, and it's going to change the main effective grip strength as a function of age. It is correct to describe it either way you want. One of those ways may be more intuitive or more be in line with your research questions. So in SAS first, I'm adding the interaction term with an asterisk in the middle. I'm asking for a model R-square F-test, so that lists every predictor in the model. On the, let's see, a couple things here. COV-B is a new option that you haven't seen yet. That gives me the asymptotic covariance matrix for the fixed effects. That's the thing that we need to compute regions of significance, which we talked about at the end last time. It's also the asking for a data set of predicted values, and it's saving the fixed effects. That's what the ODS output here does, and saving the COV-B as SAS data sets so that I can manipulate them and make them have math done on them. Let me skip ahead. Here's the analog in Stata. So single hashtag creates an interaction term between age and grip strength. SStat VCE is how you get to your asymptotic covariance matrix in Stata. That's the analog of COV-B. Predict, this is the new variable that is going to be added to the current data set. XB means use the fixed effects only. I'm also using that column to correlate to make a model R-square. And then these lincoms give me simple slopes, which we'll talk about in just a second. Those are analogous to what we have up here, these separate estimate statements in SAS. Okay, with me so far? So everything that we have up above these estimate statements would give us enough information to know whether or not the new interaction term is significant and whether it's making its constituent main effects more positive, more negative, less negative. To better describe the interaction, it is common to calculate simple slopes at high, medium, and low values of the interacting variables, as well as to plot those predictions. So that's what I'm asking for next. So here's my model equation at the top of the page. If I want to estimate, the age slope for any level of grip strength as the interacting variable, what am I going to get by default? What does beta 1 mean in the context of this new model? It's the age slope for what kind of person?
Average grip.
Average grip, so grip of 9 in this case, which is the new 0. So that's the one I get by default. That is given by this middle line right here. To figure out how to get any other value for what beta 1 would be for other values of grip strength, we take the same formula we used last time. Anywhere in the equation you see age, pull it out, and then factor. So I have a minimum of beta 1, and I also need a beta 6, because that tells me how to get the age slope as a function of grip. So what these syntax lines then are calculating is this term in parentheses next to age. I need one beta 1 plus however many beta 6s that go with the grip strength value that I'm asking for. So if I want grip strength of 6, I fill in a -3 relative to 9. 0 gives me 9, and 3 gives me 12. Going the other way, if I want the simple effect of grip strength at any age, beta 2 by itself gives me what it is at age 85. If I pull all of the grip strengths out and factor grip, the term in brackets here is what goes into the statements. I need one beta 2, so that's what the grip 9-1 stands for, and I need as many ages as the age that I'm going for, multiplied by the interaction term. This down here is how I ask for predicted values for every combination of age and grip, plus or minus and medium. That's why I do fake people, so I don't have to write all of this out. That is done by margins right here. So this is why Stata wins. You see that one line I have highlighted on the bottom? Margins? You are allowed to ask over a range. So what this means is that I'm starting at -5 in increments of 5 and going to 5, and then also starting at -3 for grip, increments of 3 going up to 3, holding those constant. That creates all possible combinations of the two that I had to write out up here. The lincoms look remarkably similar to SAS, except that we have the actual multiplication rather than just the 1 being by itself. For instance, it's times 1, and then we have plus signs in between the terms to show that it's literally a linear combination. Yeah. So this right here, blow this up a little bit. It's asking for predictions over a range of predictor values. It's start from -5 in increments of 5 inside the parentheses and go up to 5. So this gives me -5, 0, and 5. If I wanted -5, -4, -3, all the way up to 5, I change the middle parenthesis to be a 1 in increments of 1. So up above, I had to write out every specific value that I wanted. This is like a loop, basically. It loops over it. It means make there fewer lines in the output between them. Yeah. This margin's right here. Have you seen dy dx before? Any Stata folks? No? Yeah, it's the derivative with respect to x is what it's the idea of simple slopes. So this is asking for the simple slope of grip strength at these levels of age. So that 1 margins replaces the 3 lines above it. So yet another looping type functionality that I really like about Stata that SAS does not have. But I write the 3 lines out so you can see more directly what it's asking for. So the other margins up here, it's giving you the simple effect of age looping across these values of grip strength instead. So it's the opposite. And then last but not least, the last margins that I asked for here, which are the predicted means for each of these different types of people, it's going to make me a picture. Margins plot. And then we have SAS output, but the Stata output looks remarkably similar. Okay, so questions on the setup. All right, let's see what happened. So first thing I'm going to point out, in SAS, because I had read in those 9 extra fake cases, it lets me know that that's the data set it started with, that only 550 observations got used, because those were the ones that actually had outcomes. So when it came to estimating the model, it kicked out my fake people. When it comes to estimating predicted values for them, it keeps them. So this right here, 86, that's my variance left over in cognition. Fixed effects. In SAS, the intercept is listed first. It's called the constant in Stata, listed last, but otherwise they'll be in the order you specified them. So this intercept is the "you are here" sign. For what kind of person do we expect a cognition score of about 29? Age 85. Male. Grip 9. No dementia. Yep. So Does the definition of the intercept change from adding this new interaction term? Nope. The value of it changes because the model has changed, but in terms of who the intercept refers to, it's still age 85 and grip 9, just like it was when they were only main effects. Likewise, these three effects right here, the difference between men and women and the difference among the dementia groups, those values may change because the model has changed, but what they mean is the same. Are these conditional or unconditional? Unconditional. Are they marginal or are they simple? Marginal. This is the gender difference for any kind of person. These are the dementia group differences for any kind of person. So we don't have to use conditional language the same way that we will for age and grip strength. So let's do the interaction term. It's significant. The interaction term itself is positive, but what it does depends on the direction of the main effect. So if we start with age, the simple main effect of age of minus 0.33, that is the change in cognition for a 1 unit difference in age. So cognition is lower in older people, right? But that's specifically in what kind of person? Grip 9. Our interaction term then, which pattern is this? What is this age by grip strength interaction doing to my age main effect? This is a less negative, yeah. So is it making it stronger or weaker as grip is higher? Is the age effect getting stronger or weaker in stronger persons? It's weaker, less negative. Less negative or less positive implies a smaller effect. So for every additional pound per square inch, that's what a unit of grip is, that age slope itself of minus 0.33 becomes less negative by 0.12. The age slope changes per pound of grip strength by this much. Let's go the other way. Simple main effect of grip. For every additional pound of grip strength you can squeeze on the little squeezy jobby, your cognition is expected to be higher by 0.6, specifically in age 85. What does the interaction with age do to it? This is a more positive. So the effect of grip is stronger in older people and weaker in younger people. So then we get the estimates down here that I asked for. These are known as simple slopes. So the first three show grip strength as the moderator of the age slope. So the middle one is the one that we get directly from the model. It's the age slope when grip is 9. And as we would expect, it is less negative in stronger people, which also means it is more negative in weaker people. Going the other way, with age as the moderator and grip strength is the slope we care about, the middle one is what the model gives us as the main effect of grip. The main effect of grip becomes more positive, stronger in older people, and less positive, weaker in younger people. So we can see also each of these simple slopes. We could have calculated these ourselves based on the model coefficients, but what is harder to calculate without errors is the standard error and the p-value that goes with it. So we know, for instance, that age matters in people of average strength. That slope is significantly negative. But it doesn't matter, age does not seem to matter in people of above average strength. So at some point between 9 pounds and 12 pounds, this age slope becomes non-significant. Can we figure out where that is? What's it called when we try to figure that out? Do you remember? Starts with an R.
Regions.
Yeah, regions of significance. Likewise, I could talk about the same thing down here. The grip strength slope is significantly positive at age 85. At some point between age 85 and age 80, it becomes non-significant. We can find where that happens too. And then here are the predicted outcomes for my fake people. This is from the estimate statements, and then this is printed from the data set. And here's my picture. 2 pictures, in fact. So the best thing that you can do when you have an interaction that you want to explain is to make a picture. Traditionally, the variable that you think of as the slope you're interested in goes on the x-axis, and the moderator is shown by different lines. So in this case, this picture would have age as the unit of care and grip strength as the moderator. So the intercept is the middle square here, center square, for those of you who remember what tic-tac-toe, that show? No? You know what tic-tac-toe is, right? There used to be a game show where people would answer trivia questions, and there were people sitting in the squares, and like center square was like the big one. Like you were really important if you were in center square. So center square, right here. That's my intercept. The regression line shown on the x-axis, that's my simple main effective age that comes from the model. The distance between these middle markers conveys the grip strength effect that is given by default in the model. You'd have to figure out what it is per unit because these are 3 units apart, but this idea is what's given to you. So the interaction term you can either think of as how the age slope becomes more negative in weaker people, or you can think of it going this way as how the grip strength effect diminishes in younger people and is enhanced in older people. Either way. Same idea if you want to spin the picture on its axis. So here's Cove B, an extra piece of output. This is what's necessary to calculate the regions of significance. The diagonal of this matrix is the standard error squared for each of your fixed effects. The off diagonal is the covariance across your fixed effects. And I have highlighted in here the numbers that you would need to do the calculations. So I wrote a macro in SAS that does this for you. There is also, I also made an Excel sheet that does this for you. And I put that in your packet with all the other data, syntax, and output files. Open that up. This works, by the way, for higher order interactions as well. So here's the things that you would need to tell it. There we go. So we need, if I'm thinking of grip strength as the predictor first and age as the moderator, that's one way I can go. We need the fixed effect for the predictor's effects standard error squared, the interaction fixed effect, its standard error squared, and the covariance of the predictor with the interaction term, as well as the centering value of the moderator. So the fixed effects come from the solution for fixed effects, the standard error squared, and the covariances come from that Cove B matrix that I just showed you, right here. So the output then calculates the regions of significance for the centered variable as well as the uncentered variable. Go back to the handout here where I have it translated. So for instance, if I'm focusing on grip strength as the predictor and age as the moderator, these are the boundaries that I found. So this is the point where it shuts off one way or the other. So we know that the effect of grip strength in this case is going to be significantly negative anytime you are below 70.19 years, non-significant between 70 and 82, and then significantly positive after 82. So this, basically 80, it's significantly, let's see, go this way, significantly negative anywhere past 82. It will be significantly positive anywhere past, I'm saying it backwards. Let me try that again. Let me go back to this. Here we go. Significantly negative. There we go. So, 82 is where it turns on and is positive. So that is consistent with finding a significant effect at 85 and at 90. Anywhere past older than 82, there is a positive effect of grip strength. Between 82 and 70, it's non-significant. And anywhere past 70 below, it's significantly negative. In this sample, we don't have anybody down there. So there's a write-up for this in chapter 2 of the book. I try to tie it to the proportion of the sample that's above these cut points. So for most of the sample, there's going to be a positive effect of grip strength because most of the sample is above 82. Question?
This might not be the right time to ask this question, but would that be a reason why like an interaction term might be significant but the main effect isn't?
Because it's which main effect?
Because it's age. Because it's not a meaningful age.
Yeah, so I mean these are three different equally valid main effects of grip, right? One is non-significant and two are significant. They're all implied by the interaction. So yeah, the one that I happen to get from the model is the middle one because I chose 85 as my centering point. Yeah, light bulb?
Solves a lot of things, yeah.
Yeah. So have you had this situation where main effects were not significant and then you're like, what do I do now?
Yeah.
Yeah, it's because it's no longer the main effect. It's one of an infinite many.
How are you determining that value is 82? And maybe you said it earlier, but I don't see it.
So the calculations are a little bit onerous. Let me show you where they come from. This, basically. So what this does is try to use this formula for what the t-value is for testing a slope. It's the slope over the slope standard error gives you t. It works backwards. Given known t's of plus or minus 1.96, it tries to find the slope that goes with that t. And so then you can figure out the point on the other variable where that's significant or not. So it comes from knowing those estimates, because you have to be able to compute what the slope is, and then also its standard error, which comes from this. That's the extra part that you need the information in code B to be able to get. So rather than doing it by hand, because these numbers get really small and you can lose precision, I wrote a macro to do it in SAS, and I'm sure you could do the same thing in Stata if you knew how, or R for that matter. I wouldn't be surprised if there's already an R package to do this. Yeah.
Is it meaningful to search for the region of significance even though the main effect and the interaction are both in the same?
In this case, the interaction is significant.
Yeah, but like in other cases, what if the interaction is not significant? Is it like necessary for us to still calculate the region of non-significance?
You would have to work really hard to defend yourself in doing so, because a non-significant interaction means they really don't differ. You could maybe cry power and say you're going to do it anyway and use very like exploratory kinds of language to make it sound like it's okay that you're ignoring the significance test. But yeah, in theory, this is a gatekeeper. The significant interaction is a gatekeeper to figuring out the values of the moderating variable at which the simple slopes turn on and off in each direction. Yes, side note, for a long time, the APA manual, they had an example of like a table from regression that you should have. And they had an interaction example where they had the main effects from a main effects only model And then they had a model that had the interaction in it, and they actually didn't report the main effects again because they were trying to be like succinct. That is wrong, because it's not the same main effect anymore. It's the conditional main effect. And if you've mean-centered your predictors, the conditional main effects will be pretty close to what they were before, but not if you didn't. So if you picked like a more extreme centering value, like maybe the minimum of each of these variables instead, that's a perfectly valid choice to make. The main effects are gonna jiggle. So yeah, to get yourself out of that situation where the interaction is significant but the main effects aren't, you'd want to figure out when the main effects would have been significant. And this simple slopes works up to a point, but these values are arbitrary, right? So they're less useful, I think, than calculating the region under which these things would be expected to happen given the model. So let's do the other one then. If I switch which is my moderator, and I talk about the effect of age instead, my regions of significance are 9.6 and 18.5. So let's go back up to the picture then to put that in context. So anything above 9.6 is the cutoff. That's going to be, what? Make sure I say this right. The effective age will be negative, significantly negative. Anything of grip strength below 9.6. So that's like just above this line, anything down. From 9.6 all the way up to about 18, it's non-significant. And at 18 and above, it's positive. Now, no one in my sample is at 18. I've never done this test, but I think that'd be pretty high, particularly amongst this population. So that describes then, for most of the sample, the effect of grip strength, or excuse me, the effect of age is negative, given the values of grip strength that we've observed. Questions? So then wrapping up the rest of this, R square, two different ways to calculate it. In your first homework, which I'm just about ready to post for you, I'm going to have you do it this way, proportion, reduction, and error. So it's, what was the variance from the empty model with no predictors? That was 120.77. What is the residual variance now? How much is still left? Divided by the original. So that's a reduction of 28% relative to the original. And the calculating the predicted values and squaring them agrees to about the second decimal place. How are we doing? Are you still with me? Awake? Do we need to get out of our chairs and stretch? I'm not actually kidding. Should we get up? Can you humor me? Everyone stand up out of your chair for a second, please. You know, sitting is bad for you, right? That's why everyone has standing desks. Do you know that I'm never going to have a standing desk? Do you know why? Because I got my PhD so that I've earned the right to sit the hell down while I make my money, right? I'm not waiting tables anymore. I'm not stuffing shoelaces into shoes at Walmart. No, I'm not making bagel sandwiches. You know, all the things I had to do once upon a time while I was standing up with a name tag. I'm not standing up anymore, and I'm not having a name tag. But then, of course, I'm up here, right? So I could sit down, but I feel like this is like a stage, you know, and I get my stage persona on. But yes, thank you for humoring me. So this wasn't so bad, right? Two-way interactions? What about three-way interactions? Yeah. We can do three-way interactions. Three-way interactions are just as easy as two ways. So let's do a little bit of practice with those. Going back to slide 16 in example or lecture 2B. So just as two-way interactions take their main effects and moderate them, more positive, less positive, more negative, less negative. Three-way interactions do the same thing to the two ways. So it's an order of inference higher, but otherwise it's the exact same principle. So let's practice a bit. Let's say that I have an effect of x, simple main effect given by a model of 1, an effect of z of 0.5, an effect of w of 0.2. And this is a model that has a three-way interaction among those three variables, which means that not only do I have the three-way, I also have to have the two ways underneath it and the main effects. So everything. So new rule. Two-way interactions, because they are nested within a three-way, are conditional. So the x by z interaction here, if the coefficient is 0.1, that is specifically when the third variable, the interacting variable, is 0. So what would we say here? For every 1 unit change in x, what happens? According to the interaction. I'll start you off. Slope of z becomes, yeah, this is, the whole page is more positive. The question is getting the which letters go with it, right? How about if we go this way? For every 1 unit change in z, slope of x, dot, 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 becomes more positive by, I'll finish it off, 0.10. Yep. Dot, 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 ditto. How about this one? For every 1 unit change in x, what happens? Of w becomes more positive by 0.01. This one? X. There's x. Dot, dot, dot. Slope of w becomes more positive by 0.05. This one, z dot dot dot. Now, the new part. For every 1 unit change in x, what does the three-way interaction say happens? Yeah, the two-way interaction, I'll call it two-way slope of, it's going to be z by w or the others, right? Becomes more positive by 0.001. How about this one? Change it. X and the missing one, right? X and w?
Yeah.
Yep. Dot, dot, dot. And last but not least, x by z. Yeah. So three ways adjust the two ways adjust the main effects adjust y. See? Same rules, just a level of abstraction harder. So how would we write estimate statements to get these things then? Let's practice that. So here's my equation. I've got beta 1, 2, 3 for the main effects of each variable, beta 4, 5, 6 for the two-way interactions, and beta 7 for the three-way. So I am going to show you how to do equations in PowerPoint and Word. If you hit Alt and equals, you get the equation editor. So the simple main effect of x, I know, is going to start off with what? Yeah. At a minimum, I need beta 1, right? To get to what the main effect of x is. So I'm in the equation editor. If you do slash and then the symbol and hit the space bar, it makes the symbol for you. I know, cool, huh? And underscore, if you want a subscript, like beta 1, hit the space, and it jumps down there. So I need beta 1, plus, what else do I need to get the simple main effect of x for any combination of the other variables? I need a 4 all by itself or times something? Times w. What else? Beta 5 times, I need z, yep. It's the other one. You guys are picking up the, anything else? Yep, gotta have, that's got an x in there too. Beta 7 times what? Yeah, we're gonna go w and z. Doesn't matter, but it's in the same order as written otherwise. There. So that means that if I want to be able to predict what the model says the effect of x is going to be, I have to give it values for w and z to put here. It's conditional on both at the same time. How about the simple effect of z? What do I need to change? That's a 2. Do I still need beta 4? Nope. Yeah, I need, let's go swap it out for 6, right? And do I need 5?
Yes, 5.
And do I need beta 7? Do I need to change the letters?
Yes.
I need to swap out z, because that's the slope I'm going for x, how it's moderated. And last but not least, w, beta 3. Do I need this one still? That one needs to go to x, yep. Beta 5.
6.
Yep, that needs to go to beta 6. And that's z, that's okay. And how about beta 7?
X, 5, 6.
Yep, swap that guy out for x. Now the new part. Simple two-way interactions. X by z. What are all the terms here that have x by z in them? Beta 5 is the first one. Hey, stop that. Beta 5. Anything else? Beta 7. Times what? W, yeah. How about x by w? That's 4. Beta 7 still? But times z, yeah. And last one, 6. And the one that's missing, x. Yeah, see, not so hard, right? So the same thing could happen. You can have a significant three-way interaction and have nothing else significant because it depends on where the model is centered. It could totally happen. All right, so that's the summary of that. Let's see it in action. Adding a couple terms to the model here. So I'm adding an interaction of gender by dementia group so that it matches the model in the book. We'll talk about that in the next example. And I'm also adding age by gender, grip by gender, and age by grip by gender. So those three are the ones that we're focusing on. In order to show a three-way interaction of grip, age, and gender, I have now more big people because I have to show high, medium, and low for both men and women. Here's my model. So I've underlined the new terms. So I have 3 different multivariate wald tests here that I'm asking for based on this model. First one is the overall model, R squared. This is the one that Stata gives you by default. I'm adding this here for completeness, in which I am listing every single effect in the model and giving you 1 for the coefficient after it. That's because all of these variables are being treated as continuous. The model R squared change from the sex by dimension group is those 2 new interaction terms, 2-degree freedom test, and the R squared change from the 3 terms that I added on the last line. So this previously you would have had to have done in steps, like in a sequential regression. This gives you the same result from one model. Simple main effects of each of my predictors, age, grip strength, and gender. Doing just what we did before. Pulling out from the equation all of the terms that have age in them. Factoring out age. And now we're writing estimate statements for the compound term in brackets. So because age interacts with grip strength and with gender, and with both of them at the same time, at a minimum, I need 1 beta 1. I need -3 beta 6s, because that's the grip strength I'm plugging it in for. If I want it for men, then I don't need any of the beta 9s. And if it's 0 for men here, then the 3-way interaction term goes to 0 as well. If I want it for women, the last 3 lines then fill in a 1 for beta 9, and then coincidentally pick up the value multiplying that 1 through with the other term here. So every term in the model, every fixed effect that has age in it has to be included here or it's held to 0. But this will tell you what the age slope would be for any kind of person. Same thing with grip. The only difference is that it's every term that has grip in it, and we're instead filling in the values for age and gender. And then the simple main effect of gender, filling in values for age and grip as well. So stare at that for a second, see if the pattern makes sense to you. Last but not least, simple 2-way interactions. Age by grip differs by gender. So we can have an age by grip interaction for men, for women. The 3-way interaction term tells us whether that age by grip interaction differs between men and women. Likewise, we can have a sex by age interaction at any level of grip strength. The 3-way interaction also tells us whether sex by age differs as a function of grip strength significantly. Last but not least, grip by gender is the interaction term. The model tells us what it could be at any age. The 3-way interaction tells us whether grip by gender changes over age. So 3-way interactions have 3 possible interpretations. You just get to pick which one you'd like to focus on. But this gives you the means to do them all. And so this is the Stata code that goes with it. Similar in structure. Again, just changing out the signs here for pluses and multiplying things. Okay. Questions on the syntax? All right, let's practice interpreting then, because that's the hard part. Plugging in numbers is something everyone here is probably pretty good at. Otherwise, you wouldn't have self-selected into this class, right? Coming up with the words that go with the numbers, that's much more challenging. Just takes a lot of practice. So let's practice, shall we? So I'm going to highlight 3 things here to step us through. The three-way interaction that we've added is not significant. Just pretend it is so we can talk about it, okay? I know you know the difference. I want you to know what to do with the coefficients no matter what happens. Although in reality, you might look at this and go, I didn't want to have to talk about it. But this is like 0.09, right? This is, you know, you could maybe wiggle your way into talking about that. Like it's trending. My favorite term for this, by the way, is approaching significance. Because it makes it sound like if you just came back later, it would be there, like a cake that's rising. Like it's not done yet. You know, it's approaching significance. I'll just let it go for a little while longer. But yeah, let's call it approaching. Why not? So I've got age is the thing I'm caring about here. Grip strength is the moderator, and then sex is the moderator of that. So let's do one. Age 85. This is the change in cognition per year of age for what kind of person? Men who are men who are 85? No, I'm pointing to age. It can't be men who are 85. It's conditional on the other ones. Grip. Yeah, it's only conditional on itself if it's a nonlinear, like a quadratic effect. So yes, this is the age slope for men of average grip strength. In that type of person, age is a significantly negative effect. So age is bad for you. Well, negative means like if the outcome is something that's bad and you reduce it, that's a good result, right? So I'm just trying to put this back in context. The outcome is cognition, in which higher is better. So this is saying that older people have diminished cognition in this subset of people of average grip strength who are men. Okay. Now, what does the two-way interaction of age by grip say that grip does to that age slope? Less negative in stronger people. For every pound stronger you are, that negative age slope becomes less negative by 0.23, significantly even. Now, is my sentence done, or do I need to qualify it further? In men. This is in men only. So, age is bad for you. Age is less bad if you're stronger in men.
Was it age has less of an effect if that was it? Or how did you phrase it, like specifically?
This is, so the age slope becomes significantly less negative in persons who are stronger. So translating that into sort of regular language, age is bad for you. The deleterious effect of aging, how's that? Age is bad for you. Age is less bad if you're stronger. Grip is a mitigating factor or something like that.
Why aren't you interpreting that? I thought it was also conditional on dementia.
Not in this case, because dementia doesn't interact with age. Dementia does interact with gender, and so this gender effect is conditional on dementia, but age is not. So age is bad for you, less bad if you're stronger, but that's only in men. Now let's pick up this one. What does the three-way interaction do to this two-way? This is a less positive. So this one is only for men. This three-way interaction says how that two-way interaction differs in women. So it makes it less of an effect. So we'll wrap this back up starting here. Age is bad for you. Age is less bad if you're strong, if you're a dude. But the extent of that strength benefit is diminished in women. The extent of is a great way of phrasing leading into a two-way interaction. The extent to which grip strength is a protective factor is almostly significant different in women. It's reduced. You could also go age to gender to the three-way. That one's a little harder because it switches signs twice. Age is bad for you. Age is slightly less bad for you in women. The extent to which age is slightly less bad in women is reversed in stronger people. So it starts out being positive. This interaction term is going to drag it negative real quick because this is near 0. That one's a little trickier. Let's do this one. Nope, changed my mind. I want to do this one. Grip to gender by age. Okay. So, being strong is good for you. In men who are 85. What happens to that simple main effect of grip in women? Less positive. So the extent to which grip is good for you is lower in women than men, non-significantly, but whatever. Now, what does age do to that? More or less. Yes, correct. Yes. The extent to which, we'll say, the effect of grip is diminished in women is enhanced in older ages. I will take more or less. It's more or less in older people. And this is the point at which your reader goes, what? And then you say, see figure 3. So this one is easy to come up with a plot because my third variable is a grouping variable. So I've got one picture for men and one picture for women. So age by grip has a bigger interaction, more or less parallel in men than women. That's one of the patterns. You could focus in on any of the lines or any of the differences and talk about how they differ as a function of the others. But the key idea is that the model tells you the three-way interaction says whether each of its constituent two-way interactions, so these three right here, age by grip by gender, grip by gender, this equally says whether each of those is moderated by the one that's missing. So you can talk about it any of those three ways. So this gender effect right here, given the model, it is extra conditional. So it is specifically for people without dementia because of that sex by dementia interaction. It is also for 85-year-olds who have 9 pounds of grip strength. So that one has extra. How about these main effects of dementia? Are they conditional? On what kind of person? On men. Are they also conditional on age 85 or grip 9? Nope. Not because we don't have those interactions in the model. Yep. The model is back up here in terms of the equation. You can tell what all is in it though if you look at the list of fixed effects. So in this case, I have these two main effects of dementia group. They go with main effects or interactions with gender.
Are you asking me?
I'm telling you with the question at my voice to see if you're following. How's that? So these two main effects, without knowing the full list, you wouldn't know what they're conditional on. but the rest of the list gives these context. So if nothing else was here, like if you just had main effects in the model, all of these would be unconditional. Like this would be the age slope for everybody, the grip slope for everybody, the gender difference for everybody. Once you start adding these interaction terms, what these main effects
Oh, because
indicate?
they're not included in the interactions below. Is that okay?
Yeah. So we know that, for instance, age is not conditional on dementia group because it's not involved in any interactions with dementia group. We know that grip is also not conditional on dementia group for that same reason. Gender is the most conditional because it's involved in interaction with every single other predictor. Dementia group is only involved in an interaction with gender. So these are dementia group differences for men, but they would be expected to be the same regardless of age, regardless of grip strength. The hard part with the three-way is remembering that these two-way interactions also become conditional when you add the third. So this is age by grip in men. This is sex by dementia. These are not part of the three-way, so these are unconditional here. The last two are conditional. This is age by sex for grip 9. This is grip by sex for age 85. And the reason that I want you to know this, the reason I'm making such a big deal out of this is exactly what Kelly, is that your name? Yeah, nailed it. What she said earlier. If you have instances in which lower order terms are not significant, it doesn't necessarily mean that they don't matter. It's that they don't matter for that kind of person. The interaction means that they differ as a function of the moderating variable. So trying to figure out how they differ and explain it is then your further job. So in thinking about research questions, moderation is often a research question, but folks, when you're framing it, saying, does this variable moderate another, is not a very specific prediction, right? Does this variable enhance the effect of another? Does this variable diminish the effect of another? That's where you get into language like protective factors, for instance, or risk factors for that matter. So here's the results of all of those estimate statements that I could then use to tell the story. So for instance, my two-way interactions here, age by grip is significant for men. It's not significant for women. Which of these is the model going to give me already? The men, because that's my reference group. Whether or not it's significant for women is the extra piece of information that I don't have from the model, but the model predicts for me. Do I have anything that tells me whether these two coefficients are different? Do I know that? If 0.23 H by grip for men is different than 0.07 H by grip for women? Do I know that or not? Yep, that's my three-way interaction. I do know that. So now I have the missing piece. I know what it is for men. I knew if it differed between men and women. Now I know what it is for women. Same thing with these. These are simple slopes for the age by sex two-way interaction holding grip at specific values. Whether or not these numbers differ is the three-way interaction as well. The three-way interaction is per unit difference. Same thing here. So these will be on your first homework, by the way. There'll be some questions like that, where I will phrase things in a way that may not make it obvious whether or not you have it or not as part of your output. And so that's what you get to figure out. And there's my fake people, there's my picture, and there's the end.
Sorry,
Yeah.
could you explain what does a p-value means? Like three, not like a religious.
For these,
Going down.
going down.
Yeah.
Okay.
So the part you explained right now.
Mhm.
Like,
So for any of these things, This is the point estimate, this is the standard error. Estimate over standard error is t. Because we're using denominator degrees of freedom, it's t rather than z, although at this level it's not going to make a difference. And this is the p-value associated with that t statistic. Whether or not you care about the significance level depends on what the thing is that you're estimating. In this section, I am estimating slopes, where you would be interested to know whether or not there is an age slope that's significantly different from 0, for instance, or a grip slope or a sex difference, etc. It also gives you p-values, though, anytime that you estimate predicted outcomes. So for instance, if I had estimate statements that generated just predicted outcomes, it would test those against 0 as well, in which case the p-value is probably not as helpful. For each of these statements here, you can also add a slash and then a letter CL, and that gives you confidence intervals for each of those as well. I don't have them because I'm running out of room. That's the only reason. Stata, I believe, gives you them by default. All right. Other questions?
So I think when you talk about the significance, if the significance is not, so it's not, when it's not significant, do you think we still have to interpret the results, the two-way interaction?
If the three-way interaction is not significant?
Yeah, we should not think about it or talk about it at all.
That would be the most probably conservative viewpoint, yes, is that if the three-way is not significant, then you would remove it from the model. If for whatever reason you wanted to keep it in, you would have to provide some sort of additional argument as to why you're doing that. Low power, it was a research question you wanted to test, data for additional meta-analysis, you got to make up a reason, but yes.
So for example, like the top one group for age 80, just this page. So for the age 80 men, so it's not significant. So then for the group of age 80, we don't have to talk about it at all.
I wouldn't go that far because age 80 is an arbitrary point. If you wanted to talk about it, that's where regions of significance would come in handy, because then you could discuss at what point it goes from negative to positive and switches to be significant. So you can treat a two-way interaction or a one-way interaction the same way and calculate a region of significance with another higher order interaction term. I would be careful like honing in on these because 80 is just one possible value on a continuum. To me, it's different than talking about, say, men and women, because those were the only possible values for that variable. And so it's a subset that's readily identifiable. 80 is just one prediction on an infinite line of possibles. So I just picked it as an arbitrary point that's roughly one standard deviation below the mean. That's why.
Could you go to the small form again, like age by week for men, need to be down, need to be down. So it's like case like a age by, so like a, I know like 3 interaction wasn't significant, or like if it was significant and we still have like a similar like a key value, we could say so like the relationship between age and like the cognition ability like a change depends on like grade. For men, and like this like a difference is like significant among within men, but like because p value for the women is not significant, so actually like it means we don't have the evidence this change is not significant for women, or like it's not significant compared to men. In other words, like we don't have like a evidence to say like there is like a gender difference.
The evidence is not sufficient to say there's a gender difference here because the three-way interaction is not significant. But within each subgroup, one is significant and one isn't. Whether or not it's significant, though, is in part dictated by the size of the subgroup, right? So you have more power in larger subgroups to detect an age-by-group interaction, for instance, if there's more men than women, which I think is the case in this particular data set. But yeah, you could say that there was evidence for moderation of grip strength for age in men, but there was no evidence in women. However, our study doesn't have sufficient power to find the difference or whatever. And you'd have to calculate an effect size for that three-way interaction to be able to say that. But odds are good that's the case because it takes usually twice as much power, but twice as much sample size to find an effect size difference than it does to take that actual effect size. So one of the things that I'm adding to my book in the next round, I get to revise it, is in your output, let me find it, our friend T, you can easily convert T into an effect size, D or R, take your pick, and if you trust the T from this output, then you trust the Ds and the Rs. And so that can give you a ready measure as to just how powerful your effect is, because these are all unstandardized. There is no such thing as standardized effects in multi-level modeling that everybody can agree on the same way that they can in regression. So you'll have to come up with other ways of characterizing effect size. Converting T's into other effect sizes is one. What's called pseudo R square is going to be another, and total R square will be a third. So we've got a whole bunch. Other questions? All right, then I think we're at a good stopping point. No class or office hours on Thursday. I'll let you know when your first assignment is up. You now know everything that you need to know to be able to do it. And I'll let you know when your second quiz is up for next week. So, sound good? All right, enjoy the rest of your week, folks.